Hello, this is part 3 on our section about linear regression basics. We had an introduction in the first video and we saw a specific example in the second video. Now we want to go a little deeper in this video. So ask yourself the following question. Consider our data from the last example and let's say we didn't know the x values. If all you had was the y values and I gave you another x value and you had to predict the best y value for that x value and you didn't know anything about the data other than this list of y values, what would you choose for your prediction? Well, if you think about it, the only logical choice would be the average, what we call y bar, which for this data is about 14. And if you look at the plotted data, that would correspond to basically making a model that looks something like this. So in other words, a straight line, horizontal line, would be the kind of worst possible case that's still reasonable for a linear model. It wouldn't make sense to have a really low y value or a really high y value because, of course, that would just be making things worse. And if we didn't know anything about the relationship of the y values with respect to the x values, it wouldn't make sense to have a non-zero slope. All right, so let's see if we can find the formula using that average y value. The first thing we need to recognize is that given some y values, yi, where I goes from 1 to n, then y bar is the average. Or in other words, the sum of all the yi's divided by n. And if we're interested in what is the corresponding SSE for a model like this, we're basically taking all these distances and squaring it. All right, so imagine squaring, or in other words, if you want a visual, you could even think about kind of a square associated with each of these, right? And then we're just calculating the areas of all these squares. That's another way of thinking about it. And so that's a lot of area. But basically, the area of all those squares is known as SST. So SST would be the total sum of the squares. So in other words, the sum of yi minus y bar squared, where I goes from 1 to n. And this represents the worst possible linear model. Again, we're assuming that we're at least doing something logical, that we're not just doing a ridiculous model of y equals 1,000,000 or something like that. So this is the worst possible linear model, and then we've already seen that the best possible linear model, of course, is going to have some sort of slope, right? So something that went through most of the data in a positive way. Well, then, of course, that's going to lower the area of all those squares. And so what we can think about then is, well, how much proportionally better is that best model versus the so-called worst model? And that's what R squared is known as, is we're taking basically 1 minus that proportion. So remember SSE here, where SSE represents the best possible linear model. Now keep in mind, we use SSE as just a general measure for any model, where we take a given model and then calculate the squared error and then add it all up. So in this one, we're saying, all right, let us have this represent the actual least squares model and this represent that y bar model. And if you think about it, if your least squares model was no better than just taking the average, then that would mean that this proportion would represent a 1, and r squared 1 minus 1 would give you 0. So r squared of 0 is basically, there is no linear relationship. Because that would be saying that just taking the average y value was as good as any other option. On the other hand, The best case scenario would be is that if our linear model was a perfect relationship and there was no error. So notice if SSE equals 0, this corresponds to an R squared of 1 minus 0, which is 1. So this would be a perfect linear model. So just to make sure we're clear, this represents when SSE equals SST, and this represents when SSE is equal to 0, perfect linear model. And so what that tells us, because it's a proportion, is that R squared is always between 0 and 1. And most likely you're not going to have either extreme, it's going to be somewhere in between. But the closer to 1, the better. All right. And so R squared is known as the coefficient of determination. All right. And one way of thinking about it is that since it is a proportion, is that we can say it represents the proportion of the total variation in the y variable of data that can be explained by the linear model. Okay. So that is the coefficient of determination. Now the second formula that you need to be aware of is something known as the correlation coefficient. And we use the letter R, little r in this case, for this formula. You can see it written here. And notice it's a little bit different than our last one in the sense that there's no model represented by this formula. So notice this only involves the averages of the x's and the y's and the data points themselves. And yet we can still calculate a correlation coefficient. All right, that is different from our coefficient of determination, where here we had to calculate the linear model, calculate the SSE according to that best case scenario, and then do a proportion. Now the interesting thing is first of all, R is always between -1 and 1. And again, if R equals plus or minus 1 corresponds to a perfect linear model. So that's similar to our capital R. And if R is equal to 0, then that represents no linear relationship. And once again, the closer little r is to either extreme, the more linear the relationship is. Now, the one benefit of little r is that the sign tells us which way the slope of that line is. So positive r corresponds to a positive slope, negative r, negative slope. So that's a little bit of extra information that we didn't get. But the interesting thing in terms of why do we use little r here and capital R here, there's actually a relationship. Little r squared is actually equal to r squared. And that's true as long as the regression model minimizes SSE. So in the case of the simple linear regression that we've been doing, then there's no problem. But in other contexts where we're doing a nonlinear situation, that may not be the case anymore. But for our purposes, for this section, little r squared is equal to capital R squared, which is why you often only see one number presented, because you could calculate the other one if you needed to. One thing to be aware of is that because we're squaring a number between 0 and 1, the r squared is always going to be smaller than little r squared, or little r, I should say, because we're always squaring a number less than 1, assuming it's not a perfect fit. Okay, and then of course you also lose the sign. So this is the little more information about regression. Keep in mind, we're just scratching the surface. There's a lot more we could say. There's entire classes just about regression. And if you are interested in going into this deeper, I encourage you to check out those types of classes. We'll go a little deeper in our next section of videos, but just be aware that there is a lot more to say about linear regression, and we're only focusing on the basics to help us with the modeling process, not to be experts in the regression itself. But before we move on to another example, I did want to say a little bit more about some pitfalls of this coefficient of determination. All right, we're going to focus on that one, although what's true for one is generally true for the other. And the main pitfall is that an r squared near 1 does not always indicate a good model. Right? Or even a great, definitely doesn't indicate a great model. It may not even indicate a good model. So don't be fooled that just because you see an r squared of 0.9 or something, which generally in a lot of contexts would be great, but there are scenarios where an r squared of 0.9 or less can be misleading. And so let me give one example, and for that we will go to the spreadsheet. Okay, so here is our spreadsheet with just some simple data. As you can see, it's an exponential relationship, but we're not going to worry about that as much as just what happens if I fit a linear model to this data. So I'm going to add a trend line, right click on the dot, select add trend line, pick linear. Excel will give me the equation as usual, and it also gives me the r squared value, so I'm going to select that. And so here's our equation. And notice in one sense, this is a nice fit. An r squared of 0.87, so almost 0.9. It's relatively close to the dots. But in a more accurate way, this is totally missing the relationship of the data. And in fact, the relationship is not hard. It's just 2 to the x. But this linear model, if all we're doing is kind of blindly applying a spreadsheet, or a calculator to give us a formula and a r squared value, and we see that it's close to 1, and we just move on, then we're really missing the point. And so this is always an argument that if you can plot the data, you should, because otherwise you might miss something like this. And the residual analysis shows that, yes, there's definitely a trend to the error, and so this is not a good fit. Another thing to be aware of is that if I took away one of the data values, notice that also increases our r squared value. So to make it even better. Now, has that made this any less of an exponential fit? Certainly not. But because I have fewer data points, I have a better r squared value. Another way to make the r squared value better, and we'll see this more in the next section, is to make a more complicated model. So if we're not restricted to a linear model and wanting to make this have more parameters, then we will necessarily get a better fit almost always. And so we do not want to over bias our thinking, where just because we have a great r squared value means that that more complicated model is always better. So a lot of things to be aware of. R squared is a nice tool, but it's just one tool. It's not the final say. But it'd be helpful to do another example, and we'll do that on the next video. So we'll see you there.